Welcome to Deep Sleep Documentary, the channel where we explore the hidden wonders of our world through slow, calm narration and deep, atmospheric storytelling. In this episode, we drift across the vast expanse of the Sahara Desert, a place shaped by ancient oceans, shifting dunes, lost civilizations, and extraordinary life that survives against impossible odds. Together, we'll uncover how the Sahara was born, how sand dunes migrate like waves, how mirages trick the human mind, and how animals and nomadic tribes endure the cold desert night. We'll descend into forgotten canyons, cross stone plateaus older than human history, and look ahead to the radical science projects shaping the Sahara of the future. If you enjoy peaceful, immersive documentaries designed for learning, relaxation, and deep sleep, make sure to subscribe, tap the notification bell, and leave a like to support the channel. Now, settle in, breathe slowly. Our journey begins. The Sahara has not always been a vast, sun-scorched desert. In fact, for most of Earth's history, the region we call the Sahara was a fertile landscape, covered with grasslands, lakes, and even dense tropical forests. To understand how it transformed into the largest hot desert on the planet, we have to follow the deep timeline of climate shifts, continental movement, and astronomical patterns that slowly reshaped North Africa. Scientists estimate that the Sahara, in its current arid form, is only a few thousand years old, a blink in geological terms. But the forces that built it have been at work for millions of years. Around 20 million years ago, the African continent was already drifting north due to plate tectonics. This slow movement pushed the landmass closer to the subtropical high-pressure belt of the atmosphere, the zone responsible today for many of the world's deserts. Back then, however, the region still received substantial rainfall. Fossil records show traces of ancient rivers, hippos, crocodiles, and lush vegetation. In the central Sahara, scientists discovered petrified wood belonging to tropical hardwood trees, evidence that forests once thrived where dunes now reach hundreds of meters high. A major turning point occurred around 7 million years ago, when the Mediterranean Sea began to undergo dramatic changes during the Messinian salinity crisis. For several 100,000 years, much of the sea evaporated, altering humidity levels and wind patterns across North Africa. While the Sahara didn't become a desert yet, the climate started fluctuating more violently between dry and wet periods. Sediment cores from ancient lake beds, such as Lake Chad, reveal layers of clay and sand stacked in alternating cycles, marking long eras of rainfall, followed by extended drought. However, the most significant transformations happened much later, during the last few 100,000 years. This is when Earth entered a series of glacial and interglacial cycles driven by subtle but powerful changes in the planet's orbit. These cycles, known as Milankovitch cycles, affect how much solar radiation reaches different parts of Earth. Every 23,000 years or so, the tilt and wobble of the planet shift, strengthening or weakening the African monsoon. When the monsoon intensified, rain reached deep into the Sahara, turning the desert into green savannas. When the monsoon weakened, the region dried, dunes spread, and the desert resurfaced. This alternating pattern created what scientists call the Green Sahara periods. During these humid phases, which occurred repeatedly over the last 300,000 years, the Sahara was filled with enormous lakes, wetlands, and vast grass plains. Satellite data has allowed researchers to identify ancient shorelines of megalacs that covered tens of thousands of square kilometers. One of the largest, Lake Megachad, at its peak was larger than today's Caspian Sea. Evidence also shows that early human populations lived along its shores, leaving behind tools, pottery, and engravings depicting giraffes, elephants, antelopes, and other animals that can no longer survive in the region. These green Sahara periods were not just wet. They were biologically rich. The region hosted migrating herds, predators, and early human settlements. Cave art found in Algeria's Tassili Nosha, some of it more than 10,000 years old, shows scenes of swimming people, domesticated cattle, and rivers full of life. These drawings are powerful testimony that the Sahara was once a thriving habitat, nothing like the barren landscape we see today. Geological surveys have confirmed this by analyzing pollen grains preserved in sediments. These microscopic fossils tell us that savanna grasses, acacia trees, and even freshwater plants once dominated areas that currently receive less than 50 millimeters of rainfall per year. But around 5,500 years ago, the monsoon began to weaken dramatically. This shift aligned almost perfectly with changes in Earth's orbit. As solar radiation patterns changed, rainfall systems retreated southward toward the Sahel. Without regular rains, vegetation died out, exposing the soil beneath it. Wind erosion took over, carrying dust and sand across the region. Over centuries, dunes expanded, lakes evaporated, and the rivers that carved through North Africa dried into ghostly channels known as wadis. What had been a green world slowly hardened into the Sahara we know today. Scientists still debate whether human activities played a small role in accelerating this drying. Some researchers argue that early pastoralists, who grazed large herds of cattle, may have reduced vegetation cover enough to speed up desertification. Others believe the shift was entirely natural, driven by orbital mechanics and climate feedback loops. Regardless of the cause, the transition was irreversible on human timescales. The Sahara locked into its desert state, maintained by the strong subtropical high to pressure system that blocks rain-bearing clouds from reaching the region. Even today, the Sahara continues to grow and shrink, but at a much slower rate. Modern satellite measurements show that some regions are expanding while others contract depending on rainfall cycles. One of the most surprising discoveries of recent decades is the massive volume of groundwater hidden beneath the desert. Deep aquifers, remnants of ancient lakes and rivers, store enough water to fill several modern seas. Countries like Libya have drilled into these reserves for large-scale irrigation projects, although scientists warn that this fossil water is not renewable on meaningful timescales. These aquifers are relics of a greener Sahara that existed thousands of years before recorded history. The Sahara also plays an important role in global climate systems. Each year, strong winds lift more than 180 million tons of Saharan dust into the atmosphere. This dust crosses the Atlantic Ocean, fertilizing the Amazon rainforest with minerals like phosphorus and iron. At the same time, dust in the atmosphere helps regulate temperature by reflecting sunlight. Researchers studying climate models have found that changes in Saharan dust emissions can affect hurricane formation, rainfall patterns, and even monsoon strength in West Africa. In other words, the Sahara is not just a passive desert, it is an active climate engine. Understanding how the Sahara formed helps scientists predict how future climate changes might reshape the region once more. Some models suggest that in tens of thousands of years, orbital cycles may again strengthen the African monsoon, potentially turning parts of the desert green. But for now, the Sahara remains one of the harshest environments on Earth, an enormous fossil of past climates, shaped by slow but unstoppable natural forces. Its dunes, canyons, and dry basins are geological archives, holding the memory of forests, lakes, and ancient civilizations that lived before the sands claimed the land. The dunes of the Sahara may look frozen in time, but they are constantly moving. To the untrained eye, the desert seems quiet and still, yet every grain of sand is part of a slow, relentless journey shaped by wind, gravity, and the physics of fluid motion. Understanding how dunes form and migrate has fascinated geologists for more than a century. Today, thanks to satellite imaging, field expeditions, and detailed laboratory simulations, scientists can finally explain the life cycle of sand dunes with precision. What seems like a simple pile of sand is, in reality, a complex and dynamic geological system. Most of Sahara's dunes begin with a single grain of quartz. Quartz is a durable mineral that survives weathering better than many others. And over millions of years, mountains were slowly eroded by wind and rivers. The fragments became smaller and smaller until they formed the fine, uniform sand we see today. Because quartz reflects sunlight, the dunes can appear white, yellow, or even soft pink depending on the angle of light. In rare cases, certain minerals give dunes a reddish or violet tint, which becomes more visible at sunrise or sunset when the air is cooler and clearer. Dune formation starts when wind picks up loose sand from a flat surface. If the wind is strong enough, grains begin to bounce along the ground in a process called saltation. Each grain travels in small hops, striking the surface and knocking other grains into motion. When the wind encounters an obstacle, such as a rock, a patch of vegetation, or even a slight bump, the sand slows down and begins to accumulate. As more grains pile up, the obstacle becomes buried, and a dune begins to grow. Over time, dunes can reach massive sizes. Some, in the Sahara, rise more than 150 meters high, and the largest, known as megadunes or star dunes, can reach heights of over 300 meters. The shape of a dune depends on the direction and consistency of the wind. In areas where the wind predominantly blows from one direction, simple crescent-shaped dunes called barchans form. These dunes have a gentle slope on the windward side and a steep slope, called the slip face, on the downwind side. The slip face forms when sand accumulates to a point where the slope becomes unstable and collapses in small avalanches. This process happens repeatedly, causing the dune to move slowly across the desert. Barchan dunes can advance anywhere from a few meters to more than 50 meters per year, depending on wind strength. In regions where winds come from multiple directions, star dunes emerge. These dunes grow upward instead of migrating across the landscape, because the wind pushes sand toward a central peak from various angles. Star dunes are among the oldest structures in the Sahara, often remaining in place for thousands of years. Their towering ridges and sharp spines form some of the most iconic landscapes seen in aerial photographs of the desert. When scientists analyze the layers inside these dunes, they can reconstruct ancient wind patterns and climate changes, stretching back tens of thousands of years. One of the most surprising discoveries about sand dunes came from field expeditions conducted during the 20th and early 21st centuries. Geologists walking across dune fields noticed a low humming sound during certain conditions. This singing sand or booming dune phenomenon occurs when dry sand grains slide down the slip face in perfect synchronization. The vibrations amplify into an audible tone that can last several seconds, often compared to a deep musical note or the hum of an airplane engine. Laboratory experiments revealed that the sound is produced by the friction between grains of uniform size, which creates a resonant vibration. Not all dunes can sing, but those that do provide valuable information about grain size distribution and moisture levels. Modern technology has transformed the study of dune movement. Using satellite imagery, researchers track the migration of entire dune fields over decades. These images allow scientists to measure how quickly dunes shift, how they collide with one another, and how wind direction has changed over time. In some parts of the Sahara, dunes swallow old riverbeds and abandoned settlements, leaving only faint traces beneath the sand. In others, they reveal previously hidden geological features as the sands move aside. These slow transformations show that the desert is constantly reshaping itself, even if the changes are too gradual for the human eye to notice day by day. Field expeditions remain essential for understanding dune dynamics. Scientists travel to remote sections of the Sahara, equipped with GPS stations, drones, and sensors that measure wind speed and grain movement. One common method involves placing small stakes or flags around a dune and returning after weeks or months to measure how far they were buried or exposed. Researchers also collect sand samples to study grain composition, size, and moisture. These studies help scientists predict how dunes might shift in response to climate change. For example, if winds become stronger or more variable, dune migration could accelerate, affecting settlements and agricultural areas along the desert's edge. In addition to fieldwork, laboratory experiments play a crucial role in understanding dune behavior. Scientists have built wind tunnels that simulate desert conditions, allowing them to test how different wind speeds and grain sizes affect dune formation. High-speed cameras capture the motion of individual grains as they bounce and slide, revealing patterns that are impossible to observe in the field. Some researchers use rotating drums filled with sand to mimic avalanche dynamics on slip faces. Other experiments involve vibrating plates that recreate the low-frequency sounds of booming dunes. These controlled environments help explain phenomena that are difficult to study outdoors due to harsh conditions and unpredictable weather. Perhaps one of the most groundbreaking discoveries in dune science is the realization that dunes behave like fluid waves. Although made of solid grains, dunes move and interact in ways similar to water waves. When two dunes collide, for instance, they can merge into a larger dune or pass through one another while exchanging sand. Mathematical models, inspired by fluid dynamics, allow scientists to simulate dune movement on computers. These models are so accurate that they can predict how an entire dune field will evolve over decades. This information is valuable not only for geologists, but also for engineers working on infrastructure projects in desert regions. Roads, pipelines, and buildings can all be threatened by migrating dunes if their paths are not predicted correctly. Despite these scientific advances, many mysteries remain. Some dune fields shift rapidly, while others seem frozen despite strong winds. Certain dunes grow taller, while others flatten over time. There are also questions about how climate change might alter wind patterns across the Sahara. If monsoon systems shift or global wind belts change position, the behavior of dunes could transform dramatically. Understanding these processes is essential, as the Sahara is one of the largest sources of airborne dust on Earth, and changes in dune movement could affect global climate, agriculture, and even ocean ecosystems. For now, the dunes remain one of the most iconic features of the Sahara. They stand as living monuments to the power of wind and time. Beneath their shifting forms lies a record of ancient climates, long extinct rivers, and landscapes reshaped again and again. As scientists continue to study these silent giants, each discovery brings us closer to understanding the complex dance of physics and geology that transforms simple grains of sand into ever-moving mountains. The dunes are not just scenery, they are dynamic storytellers carrying the memory of past worlds across the desert, one gust of wind at a time. For thousands of years, the Sahara existed as an unmapped world, an immense, shifting ocean of sand where only nomadic tribes knew the safe paths. To outsiders, it was a blank space on ancient maps, marked simply with the word desert. The first explorers who tried to cross it faced a landscape without landmarks, extreme temperatures, and an environment so unforgiving that many never returned. Their journeys, recorded in journals, letters, and surviving maps, form a dramatic chapter in the history of exploration. These expeditions gradually revealed the shape of the Sahara, but every discovery came at a cost. One of the earliest known explorers was Herodotus, the Greek historian who never entered the deep Sahara himself, but gathered accounts from traders and travelers. He wrote of massive dunes, mysterious tribes, and caravans that crossed vast distances guided by stars. Although his descriptions mixed fact with legend, they represent the first attempts to understand the desert scientifically. Later, during the Roman Empire, military expeditions ventured into the northern Sahara. Roman officers documented oases, trade routes, and landscapes now lost beneath shifting sands. Their records, preserved on stone inscriptions, show that the Sahara was not completely isolated. Commerce and migration flowed across it long before modern times. But the true age of exploration began in the late 18th and early 19th centuries, when European powers turned their attention to Africa's interior. The Sahara, still largely unknown, became the target of ambitious geographic missions. One of the first to attempt a full crossing was Friedrich Hornemann, a German explorer sponsored by the African Association of London. Disguised as a Muslim merchant, he traveled from Egypt into the Libyan desert in 1798. Hornemann recorded detailed observations about terrain, climate, and nomadic cultures. Unfortunately, he vanished somewhere near Nigeria, and no one knows exactly where his journey ended. His manuscripts, recovered from travelers who had met him, offered valuable but incomplete insights. A more successful and tragic journey was led by the Scottish explorer Mungo Park in the early 1800s. Park did not cross the Sahara directly, but his quest to map the Niger River required traveling along its southern edge. His expeditions revealed the complex interactions between desert populations and the river civilizations to the south. Park's careful notes on geography, vegetation, and trade routes became key references for later Saharan explorers. He eventually died on the Niger, but his work inspired future generations to push deeper into the unknown. Among the most famous figures was René Caillie, a French explorer who dreamed of reaching Timbuktu, a city that Europeans considered mythical. In 1828, Caillie succeeded where many before him had failed. Traveling alone, disguised as a Muslim pilgrim, he crossed parts of the Western Sahara, enduring dehydration, sandstorms, and illness. When he finally reached Timbuktu, he was disappointed to find a modest settlement rather than the golden city of legend. But his safe return to Europe made him the first explorer to bring back a reliable, first-hand description of the city and the trade routes surrounding it. His diaries remain among the most valuable documents of early Saharan geography. While Caillie crossed the western routes, other explorers focused on the heart of the desert. The German geographer Heinrich Barth undertook one of the longest and most scientifically rigorous expeditions of the 19th century. Between 1850 and 1855, he traveled more than 12,000 kilometers across the Sahara and Sahel regions. Barth documented rock formations, ancient inscriptions, and cultural practices with extraordinary precision. He was the first European to record the ruins of Jerma, capital of the ancient Garamantian civilization, buried deep in the Libyan desert. His multi-volume reports are still used by historians and geologists today. Remarkably, Barth survived attacks, injuries, and disease, returning to Europe with knowledge unmatched by any explorer of his era. But exploration was not always peaceful. The desert claimed countless lives, and not all expeditions returned with success. In 1880, the French adventurer Paul Flatters led a mission to survey a route for a trans-Saharan railway. The plan was ambitious, linking the Mediterranean coast to sub-Saharan Africa by train. But the journey was doomed from the start. Flatters underestimated the local tribes' resistance and the difficulty of navigating regions controlled by Tuareg confederations. His party was ambushed, and Flatters was killed. Survivors attempted to flee north, but many died of thirst before reaching safety. The tragedy halted French railway ambitions for decades. Even in the 20th century, the Sahara remained a proving ground for explorers and scientists. The Italian desert researcher Laszlo Almasi, one of the most knowledgeable desert pilots of his time, conducted aerial surveys across the Libyan desert during the 1930s. Almasi helped locate lost oases, mapped sand seas, and documented prehistoric rock art that had been hidden for millennia. His work contributed to the rediscovery of the Cave of Swimmers, a stunning series of paintings depicting humans swimming in what is now dry desert terrain, clear evidence of the Sahara's ancient lakes. Almasi's expeditions blended traditional navigation with aviation, ushering in a new era of desert exploration. Scientific expeditions soon replaced heroic solo journeys. Geologists, archaeologists, and climate researchers began studying the Sahara systematically. They used trucks, aircraft, and later satellites to explore areas once considered unreachable. One major breakthrough came in the 1960s, when French and American researchers conducted large-scale surveys of the Tener Desert in Niger. They discovered fossil riverbeds, petrified forests, and archaeological sites revealing human activity dating back more than 10,000 years. These findings reshaped our understanding of the Sahara's climate history. What was once seen as a land of eternal dryness turned out to be a region that had oscillated dramatically between wet and dry phases. Perhaps the most remarkable modern discovery came from space. In the early 2000s, satellite radar systems detected the buried remains of ancient river systems beneath hundreds of meters of sand. One of these rivers, sometimes called the North African Mega River, once flowed across the Sahara into the Mediterranean. These hidden channels align with ancient trade routes and may explain how early civilizations navigated the region long before dunes buried everything. The discovery confirmed what some explorers had suspected. The Sahara once had a far more complex and vibrant landscape than the surface suggests today. Despite all these advances, crossing the Sahara remains a dangerous undertaking. Temperatures can reach 50 degrees Celsius during the day and fall close to freezing at night. Sandstorms can erase footprints in seconds, landmarks shift, mechanical failures can become life-threatening within hours. Yet explorers continue to venture into the desert, driven by scientific curiosity and the human spirit of adventure. Every expedition adds another piece to the puzzle, refining our maps and deepening our understanding of a region that still guards many secrets. The explorers who mapped the Sahara, some triumphant, some lost forever, transformed the world's perception of the desert. Their courage opened pathways for science, archaeology, and climate research. Today, their routes are studied using satellite images and GPS data, but the stories of their journeys remain timeless. The Sahara, vast and unforgiving, demanded everything from those who dared to cross it. Their discoveries shaped modern geography, while their struggles remind us that knowledge often comes at the highest cost. The desert reveals itself slowly, only to those willing to endure its harshness. And even now, with all our technology, the Sahara retains an aura of mystery, an endless frontier waiting for its next curious traveler. In the vast emptiness of the Sahara, where heat shimmers in layers and the horizon appears to float, mirages have misled travelers for centuries. Early explorers described seeing distant cities that vanished as they approached, lakes that dissolved into dry sand, and moving shapes that turned out to be illusions created by temperature and light. These visions were not hallucinations, but optical phenomena rooted in physics. To understand how mirages form, scientists study the behavior of light as it travels through layers of air at different temperatures and densities. What appears magical is really the result of refraction, the bending of light, magnified by the extreme conditions of the desert. At the core of every mirage is a simple principle. Light does not always travel in straight lines. When it passes through air layers of different temperatures, its speed changes. Hot air is less dense than cold air, so light bends when it enters or exits these layers. In the Sahara, where the surface can heat up to 70 degrees Celsius, while the air a few meters above remains much cooler, the temperature gradient becomes strong enough to warp entire scenes. This bending creates images that appear displaced, inverted, stretched, or floating above the horizon. To someone navigating the desert without modern instruments, these illusions can seem intensely real. The most common type of desert mirage is the inferior mirage. It forms when the ground is extremely hot and the air directly above it is much cooler. This temperature difference causes light coming from distant objects, such as dunes, rocks, or even camels, to bend upward as it approaches the ground. The observer's eyes interpret this bent light as coming from below the object, creating the illusion of a reflection on the ground. This is why inferior mirages often resemble shimmering pools of water. The desert surface acts like a mirror, not because water is present, but because refracted light creates an image identical to a reflection. Travelers who believed they were approaching a lake often found nothing but dry, burning sand. Even modern drivers on long, hot roads experience this phenomenon. On asphalt highways, inferior mirages appear as silver puddles ahead of the vehicle. The surface seems wet, but as the car approaches, the puddle recedes. The same physics applies in the Sahara, but on a much larger scale. The sheer size of desert flats allows inferior mirages to stretch for kilometers, making them appear more convincing than those seen in everyday environments. Some explorers in the 19th century wrote detailed descriptions of lakes, reflecting dunes and sky, only to discover later that their water had never existed. These accounts show how powerfully the desert can manipulate perception. Superior mirages are far rarer but more dramatic. Unlike inferior mirages, they form when cold air lies close to the ground and warmer air floats above it. This inverted temperature structure, known as a temperature inversion, bends light downward instead of upward. Superior mirages can lift distant objects into view, making them appear higher than their actual position. In extreme conditions, they can produce floating cities or mountains hanging above the horizon. These illusions, called Fata Morgana, were especially feared by early desert explorers because they were detailed and persistent. In a Fata Morgana, dunes stretch vertically like cliffs, caravans appear to hover in the sky, and distant plateaus seem to ripple or twist. The name Fata Morgana comes from the sorceress Morgan le Fay of Arthurian legend, believed to enchant sailors with illusions of islands and castles. In the desert, the same phenomenon can transform a familiar landscape into something dreamlike. During certain seasons, when warm winds pass over cooler morning air, the Sahara becomes a canvas for Fata Morgana displays. The illusions shift rapidly, often changing shape within seconds. Some explorers described seeing entire caravan columns multiplied across the horizon, their images stacked one above another like reflections in a house of mirrors. These distortions arise because superior mirages create multiple inverted and upright images layered on top of one another. Scientifically, mirages can be studied with precise measurements. Researchers use temperature probes to record gradients near the ground and laser beams to observe how light bends. Experiments conducted in desert research stations show that even slight differences in temperature, just a few degrees per meter, can produce noticeable distortion. In the Sahara, These gradients can reach extreme values. A sand surface at midday might reach 75 degrees Celsius, while the air at eye level remains at 35 degrees. Light passing through this gradient curves dramatically, creating illusions far more complex than simple distortions. Modern simulations use computer models to replicate the exact path of light rays, confirming the physics described in explorers' journals. Mirages have played a significant role in desert navigation. Before the era of GPS and satellite maps, travelers relied on the position of the sun, the stars, and the guidance of experienced nomads. Mirages sometimes led explorers off course by hiding real landmarks or creating false ones. A distant oasis might disappear behind a band of refracted air, while a non-existent lake might lure travelers into dangerous detours. Many historical tragedies, especially those involving lost caravans, may have been influenced by optical illusions. Journals describe instances where guides disagreed on a direction because one saw a mirage while another did not, depending on their height, angle, and the shifting air currents around them. Even today, mirages influence desert science. When researchers conduct aerial surveys, they must account for atmospheric distortion. Heat waves near the ground can cause satellite images to blur or stretch. Drones flying low over dunes sometimes record warped footage because the camera captures refracted light. Understanding these distortions is crucial for interpreting geological features like ancient riverbeds or fossilized lakeshores. Scientists studying distant rock outcrops often use multiple viewing angles to confirm that what they see is real and not a refracted image. The physics of mirages, therefore, remains an essential part of desert fieldwork. While mirages are optical illusions, they can reveal useful information about the environment. By analyzing the characteristics of a mirage, researchers can estimate ground temperature, air density, and humidity. A strong inferior mirage indicates extreme surface heating, while a sudden appearance of a superior mirage suggests a temperature inversion linked to shifting wind patterns. These observations help climatologists understand how heat is distributed across the desert and how air masses move throughout the day. Mirages thus act as natural indicators of atmospheric conditions, phenomena that blend beauty with scientific insight. To the untrained eye, a mirage appears magical or mysterious. To scientists, it is a demonstration of how delicate and dynamic the atmosphere can be. The Sahara, with its sharp temperature contrasts and vast flat horizons, provides the ideal stage for these illusions. As explorers learned, light in the desert is unpredictable, bending and stretching like a living thing. Mirages can deceive, inspire, and warn. They remind us that even in a place as seemingly empty as the Sahara, the environment is alive with unseen forces. And as long as travelers continue to cross these sands, the desert will continue to play tricks on their eyes, turning physics into something that feels almost supernatural. When the sun sets over the Sahara, the world changes from a scorching landscape of blinding light to a realm of cold, quiet shadows. Temperatures that reached more than 45 degrees Celsius during the day can drop to near freezing at night. For most animals, such extreme fluctuations would be impossible to survive. But in the Sahara, nightfall awakens a hidden world of creatures perfectly adapted to life in darkness. Their bodies, senses, and behaviors have evolved over thousands of years to endure the harshest environment on Earth. As the last traces of daylight fade, the desert becomes a living ecosystem shaped by silence, stealth, and extraordinary biological design. The most iconic of these nocturnal inhabitants is the fennec fox. Known for its oversized ears, often larger than its head, the fennec is a master of thermoregulation. Each ear acts like a radiator. Blood vessels lie close to the surface, helping release heat accumulated during the day. At night, those same ears give the fox a superhuman sense of hearing. It can detect insects moving beneath the sand or the faint steps of a distant rodent. Fennec foxes dig complex burrow systems that maintain stable temperatures, offering refuge from both daytime heat and nighttime cold. Their kidneys are so efficient that they require very little water, getting most of their moisture from prey such as insects, lizards, and small mammals. Another stealthy predator of the Sahara night is the sandcat. This small feline resembles a domestic cat but possesses adaptations that make it a true desert specialist. Its fur covers even the undersides of its paws, acting as insulation against burning sand and muffling its footsteps. This allows the sandcat to stalk prey silently, an advantage in a landscape where sound travels far. Its pale fur reflects sunlight and provides camouflage against the desert floor. Like the fennec, the sandcat lives in underground burrows that help stabilize body temperature. Scientific studies show that sandcats can survive without freestanding water for months, relying entirely on the liquid content of their prey. Their wide-set ears enhance directional hearing, making them adept hunters in total darkness. Reptiles also take advantage of the cooler nighttime conditions. The Sahara is home to several species of vipers, including the horned viper and the Saharan sand viper. These snakes are masters of a unique movement technique called sidewinding. By lifting most of their body off the hot sand and touching down at only 2 points, they minimize friction and heat absorption. This method also allows them to move quickly across loose dunes. At night, when the sand begins to cool, vipers emerge from shallow burrows or beneath rocks to hunt. Their heat-sensitive pits detect the body warmth of small mammals or lizards, enabling precise strikes even in complete darkness. The venom of these vipers is powerful, allowing them to immobilize prey rapidly and conserve energy, critical in a place where every calorie matters. Many insects of the Sahara have evolved to become active exclusively at night. The darkling beetle, for example, performs a remarkable behavior to collect water. It climbs to the top of sand dunes and positions its body so that moisture condenses on its shell. Fog droplets roll down the beetle's back and drip directly into its mouth. This strategy is vital in a region with almost no rainfall. Other insects, such as nocturnal grasshoppers and crickets, have developed a muted color palette that helps them blend into the shadows, avoiding the attention of predators. They feed on plants that store water in their tissues, indirectly recycling the desert's limited moisture supply. Bird species also take advantage of the desert night. While many birds avoid the Sahara's extreme heat by migrating through it at high altitude, some species stay year-round and adjust their activity to dusk and dawn. The Faroe eagle owl, one of the largest nocturnal birds in North Africa, hunts rodents and small reptiles under the cover of darkness. Its wings are adapted for silent flight, allowing it to approach prey undetected. Nightjars, with their cryptic plumage and wide mouths, skim low over the ground, catching insects warmed by the last remaining heat of the day. These birds depend on minimal water and survive by optimizing their energy usage, a common strategy among desert dwellers. One of the most astonishing night specialists is the jerboa, a small rodent with long hind legs and an extremely long tail used for balance. The jerboa moves by hopping, sometimes covering more than 2 meters in a single leap. This method of locomotion is highly efficient, helping the animal conserve energy and avoid predators. Its burrows remain cool by day and slightly warmer at night, creating a stable environment. Gerbos feed on seeds and small insects, and their kidneys are so well adapted that they produce highly concentrated urine, minimizing water loss. Their large eyes enhance night vision, allowing them to navigate the dunes with precision. Even the desert scorpions display remarkable adaptations to the Sahara's nighttime environment. Many species fluoresce under ultraviolet light due to chemicals in their exoskeletons. Scientists believe this may help them detect light levels or protect against the small amount of UV radiation present even at night. Scorpions are highly efficient predators, using sensitive hairs on their pincers to detect ground vibrations. They conserve energy by remaining motionless for long periods, striking only when prey comes within reach. Their metabolism is so slow that some species can survive for a year without food if necessary. While temperature is the most obvious driver of nocturnal behavior in the Sahara, other challenges also shape these animals' adaptations. The desert night can be unusually quiet, with sound traveling far across open plains. This gives predators an advantage, but also increases the risk of being detected. Many animals move in short bursts or rely on silent locomotion. Vision also becomes a unique challenge. Some species develop reflective layers behind the retina, known as tapetum lucidum, to enhance low-light vision. Others evolve heightened senses of smell or hearing to compensate. These combinations of traits create a network of efficient hunters and elusive prey, all perfectly tuned to the rhythm of the desert night. Scientific research in the Sahara often takes place at night to observe these creatures in their natural environment. Biologists set camera traps near burrows and use infrared equipment to monitor nocturnal activity without disturbance. Studies reveal that many desert animals have highly flexible behavior patterns, adjusting their activity to the phases of the moon. During bright nights, some predators hunt more actively, while prey animals seek deeper refuge. On darker nights, hunting strategies shift to rely more on vibration and sound. These behavioral changes demonstrate an intricate balance between risk and opportunity. As dawn approaches, the desert's nocturnal world retreats. Animals return to their burrows, nests, or shaded hiding places, avoiding the sun that will soon reclaim the landscape. The Sahara transforms once again, becoming silent and still. But beneath the surface, life continues to pulse quietly. The adaptations that allow animals to thrive in this environment, specialized kidneys, heat-regulating ears, silent wings, reflective eyes, are the result of millions of years of evolution. They reflect the incredible resilience of life faced with unforgiving conditions. In the Sahara, survival belongs not to the strongest, but to those most willing to adapt. And when the sun sets again, the desert's hidden kingdom will awaken, ready to navigate another night in one of the most extreme environments on Earth. For more than 1,000 years, the Tuareg people have lived across the vast deserts of the central Sahara, shaping a culture defined by movement, tradition, and survival. Often called the blue people of the desert because of the indigo dye that stains their clothing and sometimes their skin, the Tuareg are one of the most recognized nomadic groups on Earth. Their history is woven through the dunes, trade routes, and oases that once connected the African interior with the Mediterranean world. In a landscape where the environment tests every living thing, the Tuareg developed a way of life that blends adaptation, resilience, and deep cultural identity. The origins of the Tuareg trace back to the Amazigh peoples of North Africa, whose presence in the region predates recorded history. Linguistic studies place the roots of Tamashek, the Tuareg language, in the broader Berber family, suggesting a continuity of culture stretching thousands of years. Archaeological evidence indicates that early pastoral societies occupied the central Sahara long before it became the hyper-arid desert we see today. As the climate shifted and rainfall disappeared, these communities adapted by becoming mobile, following the delicate balance of pasture, water sources, and trade opportunities. Over centuries, the Tuareg emerged as expert navigators of an unforgiving landscape. Tuareg society is traditionally structured around clans, known as Kel, each with its own territory, responsibilities, and lineage. Historically, noble clans were associated with leadership and decision-making, while artisanal and vassal groups formed the working foundation of the community. Although social roles have evolved significantly in recent decades, these cultural frameworks still influence identity and belonging. Matrilineal descent is a distinctive feature of Tuareg culture. Lineage is traced through the mother, and women traditionally hold the family's most valued possessions, such as tents and livestock. This structure gives Tuareg women a respected position in community life and decision-making. One of the most iconic symbols of Tuareg identity is the tagelmust, the indigo-dyed face veil worn by men. Beyond its cultural significance, the tagelmust serves practical purposes. It protects the wearer from blowing sand, intense sunlight, and sharp nighttime cold. Studies show that indigo dye has mild antibacterial properties and helps shield the skin from ultraviolet radiation. The veil also acts as a filter against dust storms, which are common in desert regions. Tuareg boys begin wearing the tagelmust in adolescence, marking their transition to adulthood, responsibility, and honor. It becomes a lifelong companion, rarely removed in public. The Sahara has always been a crossroads, and the Tuareg were at the heart of its trade networks. For centuries, they guided caravans across thousands of kilometers, transporting goods between sub-Saharan Africa and the Mediterranean. The most famous of these were the salt caravans of the Central Sahara, particularly those linking the mines of Taoudeni in northern Mali to markets in Timbuktu and beyond. Salt, essential for livestock, food preservation, and human health, was once as valuable as gold in the desert. Caravans could include hundreds of camels, each carrying heavy slabs of salt stacked like stone tablets. The journey was long and perilous, taking several weeks through regions with no permanent water sources. Tuareg guides relied on memory, star patterns, and subtle changes in the wind and sand to navigate routes invisible to outsiders. Camels were essential partners in this trade. The dromedary camel, adapted perfectly to desert life, can travel up to 40 kilometers a day and survive for long periods without water. Tuareg camel saddles and reins were engineered for stability and comfort during long journeys. Scientific studies of camel physiology show that these animals can tolerate body temperature fluctuations that would kill most mammals, and they possess specialized red blood cells that maintain function even when dehydrated. The Tuareg understanding of camel behavior, health, and breeding reflects centuries of accumulated knowledge that made trans-Saharan trade possible. The Tuaregs' desert survival strategies extend far beyond navigation and camel mastery. Their nomadic lifestyle depends on identifying and rotating seasonal pastures, allowing vegetation to regenerate naturally. Water sources, wells, gueltas, and ephemeral streams are deeply embedded in oral tradition. Each clan knows the location, depth, and quality of dozens of wells within their territory. Many of these wells date back centuries, reinforced with stone rims to prevent collapse. Survival also depends on timing. Movements are planned around seasonal winds, rare rains, and the availability of grazing plants such as acacia, desert grasses, and drought-resistant shrubs. These strategies reflect a profound ecological understanding shaped by generations of observation. Cultural expression is central to Tuareg identity. music, poetry, and storytelling preserve history, values, and legends. Instruments such as the imzad, a single-stringed bowed lute traditionally played by women, and the tindi drum, used in communal gatherings, accompany songs that recount battles, migrations, and love stories. Oral tradition remains strong even in modern Tuareg communities. Poets and storytellers are respected figures who carry the memories of their people. Their recitations describe heroic ancestors, desert spirits, and journeys that blur the line between myth and lived experience. These stories help guide moral behavior and reinforce the bonds of the community. Tuareg craftsmanship is equally distinctive. Artisans create intricate silver jewelry engraved with geometric symbols, each with specific meanings related to protection, tribe, or lineage. Leatherwork, saddlebags, and tent decorations are dyed and embroidered with patterns that reflect the environment: dunes, stars, and desert plants. Scientific analysis of traditional dyeing techniques shows that natural pigments extracted from plants such as indigofera have remarkable longevity, resisting fading under the intense Saharan sun. These artistic traditions serve both functional and cultural purposes, reinforcing identity while providing essential everyday tools. Tuareg religion blends Islamic faith with older nomadic customs. Islam arrived in the region between the 8th and 12th centuries, carried by merchants and scholars traveling the trade routes. Over time, Tuareg communities adopted Islamic teachings while maintaining elements of their pre-Islamic beliefs, such as taboos surrounding certain animals or places. Religious leaders, known as marabouts, often serve as healers and keepers of spiritual knowledge. Their roles include maintaining peace within the community, offering blessings for journeys, and preserving sacred texts written in Tifina, the ancient Tuareg script. This blend of faith and tradition reflects the adaptive nature of Tuareg culture. Modern influences have changed Tuareg life, yet the spirit of the nomad remains. Many Tuareg communities today live in towns or semi-sedentary settlements influenced by political boundaries, climate change, and conflicts in the region. Desertification and shifting rainfall patterns challenge pastoral livelihoods, while new economic opportunities draw younger generations toward urban life. Yet the cultural foundations, language, music, dress, and tradition continue to thrive. Festivals, camel races, and gatherings help preserve the identity of the Blue Warriors even as they navigate a changing world. Despite the challenges of the modern era, the Tuareg remain symbols of endurance in one of Earth's harshest landscapes. Their knowledge of the desert, its winds, stars, plants, and animals, offers insights into human survival and adaptation. For the Tuareg, the Sahara is not an empty wasteland but a living space filled with meaning. It is a home shaped by centuries of movement, memory, and tradition. And as long as the dunes continue to shift under the desert sun, the culture of the Tuareg will remain woven into the sands, carrying the legacy of the Blue people across generations. Survival in the Sahara has always required a combination of experience, intuition, and practical knowledge passed down through generations. For Bedouins, Tuareg groups, and early explorers, the desert is both a formidable adversary and a teacher. Temperatures that can exceed 50 degrees Celsius, scarce water sources, and shifting dunes make the Sahara one of the most challenging environments on Earth. Yet people have crossed it for thousands of years, using methods that blend cultural wisdom with natural science. Understanding these survival strategies reveals not only how humans adapt to extreme conditions, but also how knowledge, patience, and observation can make the difference between life and death in a landscape that offers no second chances. Navigation is one of the most critical skills in the desert, where landmarks can disappear under moving sand, and visibility can extend for hundreds of kilometers. Traditional desert nomads navigate primarily by the sun, stars, and wind patterns. During the day, the position of the sun provides a general orientation, but its movement can be deceptive without experience. Skilled navigators observe subtle shadows cast by dunes and rocks. Even the shape of sand ripples, known as ventifacts, reveals wind direction, helping travelers determine north or south. At night, navigation becomes more precise. Desert travelers rely on bright constellations such as Orion, the North Star, and the Pleiades to maintain a steady course. Unlike daytime heat, which distorts the horizon, the cool desert night offers clear skies ideal for celestial navigation. Modern explorers often use GPS devices, but many still train in traditional techniques as backups. Electronics can fail under extreme heat, sand intrusion, and long expeditions where batteries are difficult to replace. Historical records show that early European explorers underestimated the importance of traditional navigation skills. Those who ignored local advice often became lost, disoriented by mirages or sudden sandstorms. Buried caravan trails and ancient markers carved into rocks, sometimes centuries old, serve as guides. These markers often point to wells, seasonal grazing areas, or mountain passes that are invisible from a distance. Bedouins memorize these locations and teach them orally through stories or songs, ensuring the knowledge survives across generations. Finding water is one of the greatest challenges in the Sahara, and the techniques used are a testament to human ingenuity. The desert's water sources are often hidden, seasonal, or extremely limited. One of the most reliable indicators of underground water is vegetation. Plants such as acacia trees, tamarisks, or desert palms have deep root systems that access water far below the surface. Bedouins can identify these plants from a distance and predict the approximate depth of groundwater based on their size and placement. Low-lying areas, known as depressions or wadis, sometimes retain moisture after rare rainfall events. Fine, cool sand in these areas may indicate that water lies just below the surface. Wells are crucial for survival, and many are centuries old, maintained by local tribes. Some wells reach depths of 30 meters or more. They are often lined with stone to prevent collapse. In regions such as the Enadi Plateau or the Air Mountains, travelers use gueltas, permanent pools of water trapped between rocks. These pools can persist for years, fed by underground seepage even in extremely dry periods. Explorers learn to test water quality for salinity or contamination, as some sources may be undrinkable. The tradition of rationing water is strict. Nomads drink according to need, not comfort, and travel during cooler hours to reduce dehydration. Camels, capable of losing up to 25% of their body water without harm, serve as mobile reservoirs. Heat protection strategies often draw on simple yet effective principles. Clothing is one of the most misunderstood aspects of desert survival. While outsiders might assume that minimal clothing is ideal, nomads dress in multiple loose layers. These layers trap cooler air close to the skin while shielding the body from direct sunlight. The fabric, often cotton or lightweight wool, breathes easily and allows sweat to evaporate slowly, lowering the risk of dehydration. Covering the head is essential. Traditional headscarves or turbans prevent heat stroke, reduce glare, and protect against blowing sand. Scientific studies have shown that light-colored fabrics reflect sunlight, reducing overall heat absorption. This explains why desert cultures favor white, beige, or blue garments. Shelter construction is another crucial survival technique. During long journeys, travelers use natural formations, such as rocks or dunes, for shade. In open desert plains, tents made from goat hair provide surprisingly effective insulation. Goat hair expands when wet and contracts when dry, allowing the tent to stay cool during the day and retain warmth at night. These tents can withstand strong winds and sudden temperature shifts. For explorers caught unexpectedly in the open, digging shallow pits and covering them with fabric or blankets can create temporary shelters that reduce temperature exposure by several degrees. Food sources in the desert require strategic planning. Traditional nomads rely on a combination of dried grains, dates, nuts, and milk from camels or goats. These foods are lightweight, energy-rich, and resistant to spoilage. Dates, in particular, provide quick sugars and electrolytes essential for surviving long treks. Hunting is rare but possible. Small animals such as hares, reptiles, or birds can be trapped or caught using simple tools. Edible desert plants, such as the desert truffle, which appears after rare rains, offer valuable nutrients. Modern explorers often carry compact rations and equipment to boil water, but many still learn traditional methods for identifying edible plants or trapping small animals as backup strategies. Survival also depends on understanding and predicting weather patterns. Sandstorms, known as haboobs, can appear suddenly and reduce visibility to near zero. Experienced nomads recognize early warning signs: a distant wall of dust rising along the horizon, a sudden drop in temperature, or changes in wind direction. During a storm, the best strategy is to shelter behind a dune or lie flat with the back to the wind, protecting the face with cloth. Movement during a storm is dangerous due to disorientation and the risk of inhaling fine sand particles. After major storms, dunes can shift dramatically, erasing tracks and landmarks. This is why knowledge of star navigation and natural markers is essential. Night travel is another technique used to conserve energy and reduce water loss. Temperatures can be more than 20 degrees cooler at night, allowing travelers to cover long distances with less strain. However, night travel requires strong navigation skills, as the landscape becomes monochromatic and difficult to read. Travelers listen for subtle environmental cues, such as wind direction or the sounds of distant animals. Camels have excellent night vision and play a vital role in leading caravans in low-light conditions. Their natural instincts and memory of familiar routes help guide caravans safely through vast stretches of desert. Psychological endurance is also an important aspect of survival in the Sahara. The vast emptiness, extreme silence, and monotony of the landscape can disorient travelers. Traditional cultures developed methods to manage these psychological stresses. Songs, chants, and rhythmic walking help maintain focus. Stories shared at night around small fires build morale and strengthen group cohesion. Early explorers often wrote about the mental challenge of navigating endless dunes that seem to repeat endlessly. Modern survival training emphasizes maintaining a calm mindset, conserving energy, and making decisions methodically rather than impulsively. Ultimately, the real lessons of desert survival come from those who have lived in the Sahara for generations. Their knowledge, rooted in observation, trial, and tradition, continues to guide explorers and researchers today. The Sahara may appear empty and hostile, but it rewards patience, respect, and preparation. In this immense landscape, survival is not achieved through force or technology alone, but through understanding the rhythms of nature, reading its subtle signs, and learning from the people who have mastered its challenges. For those who cross its sands, the desert becomes both a test and a teacher, offering timeless lessons about resilience and the fragile balance between human life and the environment. The Sahara is often described as a sea of sand, but in reality, only about a quarter of its surface is covered by dunes. The rest is a world of stone, vast plateaus, uplifted massifs, weather-sculpted ridges, and deep canyons carved long before this region dried out. These rocky landscapes, some of the oldest surfaces on Earth, hold clues about ancient rivers, tropical forests, and even early human migrations. To cross them is to walk across geological time itself, stepping on terrain shaped by oceans that vanished hundreds of millions of years ago. Much of the Sahara's rock foundation dates back to the Paleozoic era, over 400 million years ago, when the continents were arranged differently, and this region lay close to the southern supercontinent Gondwana. At various times, the land was submerged beneath shallow seas, which deposited layers of limestone, sandstone, and shale. These sediments would later be uplifted by tectonic forces and stripped by wind erosion, leaving behind the monumental plateaus we see today. Some of these stone surfaces have not been buried or reshaped in over 100 million years, making them among the most ancient exposed landscapes on our planet. One of the most iconic stone regions of the Sahara is the Tassili Niger, a massive plateau in southeastern Algeria. Rising steeply from the desert floor, it is composed of layered sandstone shaped by wind and water into arches, pillars, and labyrinth-like corridors. What makes Tassili extraordinary, however, is not only its geology, but its history. The porous sandstone once trapped rainwater, forming seasonal pools that allowed Neolithic humans to thrive here thousands of years before the desert expanded. They left behind more than 15,000 rock paintings and engravings depicting giraffes, elephants, cattle, and even swimmers, vivid evidence of a greener Sahara. These artworks serve as both scientific data and cultural heritage, documenting a climate cycle that transformed fertile savannas into barren rock. To the south lies another stone giant, the Hoggar Mountains, also known as the Ahaga. Unlike the sedimentary plateau of Tassili, the Hoggar is volcanic in origin. Its rugged peaks, including Mount Tahat at 2,918 meters, were formed by ancient eruptions during the Tertiary period. Over millions of years, erosion stripped away the softer outer layers, leaving behind hardened volcanic cores that now tower above the surrounding desert. These mountains create cooler microclimates where certain plants, such as Saharan cypresses and myrtles, still survive in hidden valleys. Some of these species are relicts, leftovers from wetter eras, making the Hoggar an important refuge for biodiversity in an otherwise harsh environment. Further east, the Tibesti Mountains rise from northern Chad like a fortress of black volcanic rock. This is the highest continuous range in the Sahara, topped by Emikusi, a 3,445-meter extinct volcano. The Tibesti is a place of extremes: deep craters, fumaroles, dried lava fields, and narrow gorges carved by rare but violent flash floods. Geological studies suggest the volcanic activity here may have continued into the Holocene, making this region relatively young in geological terms. At its base, ancient riverbeds known as oases cut through the stone, revealing layers of the Earth's crust that would normally lie buried deep below. Hidden canyons are among the Sahara's most striking stone features. Many of them were formed during humid periods, when rainfall was far more abundant and rivers flowed across what is now desert. Over thousands of years, water carved deep channels into the bedrock, leaving behind slot canyons that still bear the marks of long-extinct torrents. Wadi Methendus in Libya, the gorges of Timras in Algeria, and the canyons of Enedi in Chad are among the most spectacular examples. Today, these places are dry and silent, yet the patterns etched in the stone, smooth curves, scoured walls, sediment-filled basins, reveal a landscape created by forceful, persistent water. In some canyons, regueltas, or permanent water pools, remain as the last remnants of ancient rivers. These sheltered oases attract wildlife such as crocodiles, believed to be the descendants of populations that survived from the Green Sahara era. The Enedi Plateau in northeastern Chad provides another window into the Sahara's geological past. Its sandstone formations look like natural cathedrals, tall pillars, narrow bridges, and towering cliffs shaped by differential erosion. Over millions of years, wind and sand exploited fractures in the rock, carving out elegant arches and freestanding columns. Because sandstone is relatively soft, these shapes evolve continuously, making Enedi a living sculpture garden created by the desert itself. Scientific expeditions often visit the area not only for geology, but also to study the remnants of ancient lakes and wetlands preserved in the rock layers. Fossilized fish, shells, and even crocodile remains have been discovered here, proving that water once covered parts of this plateau. Some of the most enigmatic stone features of the Sahara are its desert pavements, also known as regs. These are vast flat surfaces covered with tightly packed stones, polished over millennia by wind-blown sand. Contrary to appearances, these pavements are not man-made and not leftover ruins. They are natural surfaces created when wind removes finer particles, leaving behind a protective layer of gravel. Regs can extend across hundreds of kilometers and are so stable that some have remained unchanged since the Pleistocene. They serve as a geological record, capturing ancient meteorites, fossils, and artifacts that would otherwise be erased by shifting dunes. In contrast to these flat expanses, the hamadas, barren rocky plateaus, represent some of the harshest terrain in the Sahara. With little sand and no vegetation, hamadas expose naked bedrock to the elements. Temperatures on their surfaces can exceed 70 degrees Celsius during the day, while nighttime radiative cooling drops them close to freezing. This thermal stress causes the rock to crack and peel through a process known as exfoliation. Over time, entire layers flake off like onion skins, contributing to the slow but relentless sculpting of the plateau. Explorers often describe crossing hamadas as more challenging than traversing dunes because the terrain is jagged and the heat reflects brutally from the stone. The Sahara's stone regions also preserve signs of ancient tectonic activity. Faults, folds, and uplifted strata can be seen in places like the Air Mountains of Niger, where Precambrian rocks, over 2 billion years old, rise above volcanic plateaus. These formations tell the story of continents colliding, splitting, and drifting apart. During the Paleozoic, glaciers advanced over parts of what is now the desert, leaving behind striations and deposits that still exist today. By studying these features, geologists reconstruct the long climatic history of North Africa and the shifts that eventually led to desertification. Despite their apparent lifelessness, these stone landscapes play a crucial role in the Sahara's modern environment. They influence wind patterns, redirect seasonal water flows, and create natural barriers that determine where sand accumulates. Many of the region's oases form at the edges of plateaus, where groundwater is trapped by impermeable rock layers. In some cases, fault lines allow ancient fossil aquifers to reach the surface, creating springs that sustain human settlements. Without these stone formations, the Sahara's hydrology would be radically different, and many desert communities would not exist. Today, scientists continue to study the Sahara's rock architecture using satellite imagery, drone surveys, and on-site expeditions. Each plateau, canyon, and massif offers a new piece of evidence about the Earth's evolutionary history. The desert, often misunderstood as empty and unchanging, is in fact a complex geological archive, one written in stone rather than sand. To walk through these stone oceans is to witness the remnants of vanished environments, oceans that dried, forests that disappeared, and rivers that carved their way through rock long before humans existed. The Sahara's rocky heart reveals that even the most desolate landscapes have deep stories to tell, shaped not by centuries, but by billions of years of planetary change. The Sahara of the future may look very different from the Sahara we know today. As global temperatures rise, scientific models predict that the desert will continue to play an increasingly important role in climate dynamics, energy production, and even international infrastructure. Far from being an empty, unchanging wasteland, the Sahara is becoming the focus of some of the world's boldest scientific proposals. From massive solar farms capable of powering continents, to geoengineering ideas that could reshape weather patterns, and to growing interest in desert colonization. The world's largest hot desert is emerging as a place where extreme environments may inspire equally extreme solutions. Climate scientists have long studied how the Sahara responds to changes in Earth's temperature. In the past, relatively small shifts in the planet's orbit transformed the desert into green savannas dotted with lakes and wetlands. These cycles, known as orbital precession, occurred roughly every 20,000 years and were responsible for the African humid periods of the past. Today, however, human-driven warming is altering these natural rhythms. Satellite data shows that the Sahara has expanded by roughly 10% in the last century, mostly on its southern boundary, where the Sahel region struggles with drought. If current warming trends continue, some climate models predict further desertification, with increased dust emissions and more frequent heat extremes. Yet paradoxically, other models suggest the possibility of more rainfall in certain parts of the Sahara in the distant future. As temperatures climb, the air's capacity to hold moisture increases. Combined with changing sea surface temperatures in the Atlantic Ocean, this could strengthen West African monsoons and introduce more seasonal rainfall to the desert's edges. While this does not mean a return to the lush green Sahara anytime soon, it highlights an essential point. The Sahara is not static. Its future depends on a complex interplay of global climate systems, many of which are still being studied. One of the most ambitious proposals involving the Sahara is the idea of constructing massive solar farms across its sun-drenched surface. The desert receives some of the highest solar radiation on the planet. In some regions, more than twice the annual sunlight seen in Central Europe. Engineers have long calculated that covering just a fraction of the Sahara with high-efficiency solar panels could supply electricity for all of Africa, or even significant portions of Europe and the Middle East. Concepts like the Desertec project, proposed in the 2000s, explored the possibility of building a network of solar plants and high-voltage power lines connecting the desert to major population centers. While Desertec did not fully materialize, smaller-scale solar developments in North Africa have already demonstrated the region's potential. Morocco's Noor solar complex, for example, showcases concentrated solar technology capable of storing heat and generating power after sunset. Similar installations in Egypt, Tunisia, and Algeria are expanding rapidly. As solar panel efficiency increases and energy storage improves, many experts believe the Sahara may eventually become one of the world's primary sources of renewable energy. Large-scale solar farms, however, also come with environmental implications. Some studies suggest that many thousands of square kilometers of solar panels could alter local weather by absorbing sunlight previously reflected by desert sand. The panels would warm the surface, potentially increasing convection and cloud formation. In a few climate simulations, this effect actually led to localized increases in rainfall, which could trigger vegetation growth. A surprising example of how renewable infrastructure might unintentionally influence ecosystems. Though these models are speculative, they highlight the interconnectedness of climate, land, and technology in the Sahara's future. Another futuristic concept involving the Sahara is geoengineering. Deliberate, large-scale manipulation of the environment to counteract climate change. One idea is to use the desert as a site for atmospheric experiments, such as testing aerosol particles that could reflect sunlight and cool the planet. Another proposal involves planting drought-resistant vegetation across wide areas of the desert to stabilize soil and reduce dust emissions. Some researchers have even explored the notion of artificially flooding low-lying basins like the Sahara Depression in Egypt to create new inland seas. Although these concepts remain controversial and most are unlikely to be implemented, they underscore the Sahara's role as a testing ground for ambitious scientific thought. Beyond scientific projects, discussions about the Sahara's future often touch on human settlement. Desert colonization might seem like a distant idea, but rapid population growth in North Africa has already pushed cities closer to arid regions. Advances in desalination, solar-powered cooling, and hydroponic agriculture are making desert living more feasible than ever before. Some architects envision solar cities, low-profile communities designed to minimize heat absorption and operate entirely on renewable energy. Experimental farms using solar-powered greenhouses are already working in parts of Tunisia, Libya, and Morocco, demonstrating that food can be produced in the desert with minimal water through techniques like drip irrigation and humidity harvesting. For desert communities such as the Tuareg and Bedouins, the Sahara of the future presents both opportunities and challenges. Renewable energy investments may bring economic benefits, but they also risk disturbing traditional migration routes and cultural landscapes. Water scarcity remains a significant concern, especially as fossil aquifers, which supply most Saharan oases, continue to deplete. Some future scenarios involve advanced groundwater mapping and sustainable extraction methods that balance development with conservation. As with many global issues, the Sahara's future will likely require cooperation between governments, scientists, local communities, and international organizations. Extreme science projects also include exploring the Sahara as an analog for other planets. The desert's volcanic fields, salt flats, and hyper-arid regions resemble Martian landscapes. Space agencies frequently use Saharan terrain to test rovers, drones, and astronaut survival techniques. Some research stations study microbial life in the desert's driest areas, searching for extremophiles that could survive in Martian-like conditions. These environments help scientists understand how life might persist on other worlds and prepare for future missions beyond Earth. Despite all these possibilities, one of the most critical aspects of the Sahara's future is the role it plays in Earth's atmosphere. The desert's dust is not merely a byproduct of dryness. It is a global nutrient engine. Every year, hundreds of millions of tons of Saharan dust travel across the Atlantic Ocean, fertilizing the Amazon rainforest with phosphorus and other minerals. Changes in desert size or wind patterns could influence ecosystems thousands of kilometers away. Understanding this connection is essential for predicting how the planet will respond to future climate shifts. As the Sahara evolves, so too will the biological systems that depend on its dust, from South American forests to European air quality. Ultimately, the Sahara of the future is a place of uncertainty, transformation, and potential. It may become a hub of renewable energy, a frontier for climate science, a testing ground for extraterrestrial exploration, or a landscape reshaped by shifts in rainfall patterns. What is certain is that this desert, often seen as empty and static, is deeply connected to the rest of the world. Its harsh winds, hidden aquifers, and vast plains of sunlight influence global climate, human innovation, and the future of sustainability. The Sahara has always been a place that challenges survival and imagination. In the coming decades, It may challenge humanity in new ways, not as an obstacle to overcome, but as a partner in the fight against climate change and the search for new forms of life and energy. The desert's silence hides a dynamic future, one in which science, climate, and human ambition converge on one of the most extreme landscapes on Earth. Thank you for watching this episode on Deep Sleep Documentary. Tonight, we traveled across the Sahara, a land of stone oceans, ancient rivers, nomadic tribes, hidden oases, and scientific visions of the future. If this documentary brought you knowledge, calm, or a moment of escape, please hit subscribe and activate the bell so you won't miss the next journey. Here, you'll find long, soothing documentaries crafted for deep sleep, relaxation, meditation, and quiet exploration of the world's mysteries. Feel free to leave a comment and tell me what topic you'd like to explore next. Until then, close your eyes, breathe gently, and allow your mind to drift into silence. I'll see you in the next documentary.